POSIX Threads. What is POSIX Threads? POSIX Threads, commonly called Threads, are a standardized threading application programming interface, defined by POSIX, which stands for Portable Operating System Interface. POSIX Threads provide a way to create and manage multiple threads within a single process, allowing tasks to run concurrently. A thread is the smallest unit of execution inside a process, and multiple threads together form a multi-threaded application. Threads are formally defined by the IEEE POSIX standard, specifically IEEE 1003.1c, which ensures portability across operating systems. They are mostly used in C and C++ programming, especially in system-level and high-performance applications. To safely manage shared resources, threads provide synchronization mechanisms such as mutexes, semaphores, and condition variables, which help prevent race conditions and ensure data consistency. Asterisk. How a process differs from threads. The image on the left represents a single process execution model. In this model, there is only one flow of execution. The process contains code, data, and file resources, which are shared within the process. It also has only one set of CPU registers and one stack. Since there is only one stack and one register set, only one task can execute at a time. This model is simple, but it does not efficiently utilize the CPU, especially in multi-core systems. The image on the right shows a multi-threaded process, such as one created using POSIX Threads. Here, multiple threads exist within the same process. All threads share the same code, data, and file resources, which reduces memory usage and communication overhead. However, each thread has its own set of CPU registers and its own stack. Thread creation and execution in threads. 1. Creating a thread. Use thread_create to start a new thread. Each thread executes independently in parallel with the main thread. 2. Thread execution. Each thread runs a thread function that you define. The function contains the task the thread will perform, enabling parallel execution of multiple tasks simultaneously. Thread termination and joining in threads. A. Thread termination. A thread can terminate by calling. retval can be used to pass a result back to the joining thread. B. Waiting for thread completion, joining. Another thread, often the main thread, can wait for a thread to finish using thread ID of the thread to join. retval receives the value returned by thread_exit. This mechanism ensures synchronized completion of threads and allows data to be passed back safely. Synchronization in Pthreads. When multiple threads share the same memory, issues like race conditions, deadlocks, and starvation can occur. Race conditions, simultaneous access causes inconsistent data. Deadlocks, threads wait indefinitely for resources. Starvation, some threads never get CPU access. 1. Mutex locks, mutual exclusion. Ensure that only one thread accesses a shared resource at a time. Syntax. Protects global variables, shared data structures, or files from concurrent modification. Condition variables. Condition variables allow threads to wait for specific conditions before proceeding. Syntax. They are especially useful for coordinating threads in scenarios like producer-consumer problems, where threads need to wait for resources or events before continuing execution. This slide explains parallel computing using POSIX Threads, also known as Pthreads. Parallel computing involves the simultaneous execution of multiple tasks on a single computing system. POSIX Threads are used to create multiple threads within the same process, enabling concurrency. All threads share the same address space, including program code, data, and open files. However, each thread has its own stack and its own CPU registers, which allows independent execution. Communication between threads takes place through shared memory, making it very fast and efficient. To ensure correct and safe execution, Pthreads provide synchronization mechanisms such as mutexes, semaphores, and condition variables, which help avoid race conditions and maintain data consistency. This section explains distributed computing. Distributed computing consists of multiple independent systems that are connected through a network. Each system has its own memory, its own processor, and its own operating system. Since processes do not share memory, the direct use of POSIX threads is not possible in distributed systems. Communication between systems occurs through message passing techniques such as MPI, sockets, or remote procedure calls. Network-based communication introduces latency and communication overhead. Distributed systems are mainly designed to achieve scalability, fault tolerance, and resource sharing across multiple machines. Limitations of threads. Platform dependency. Threads API is not fully portable across all operating systems. Manual synchronization. Programmers must manually manage mutexes and condition variables. Race conditions and deadlocks. Incorrect handling can cause bugs and inconsistent data. Debugging complexity. Thread-related errors are hard to trace and fix. Limited distributed support. Cannot communicate across nodes without MPI or other frameworks. Scalability restriction. Limited by the number of cores in a single machine. Applications of threads. Scientific computing, parallel matrix operations, simulations, and numerical algorithms. Image and video processing, parallel filtering, rendering, and compression. Web servers, handling multiple client requests simultaneously. Parallel file processing, sorting, searching, and aggregating large datasets. High-performance computing, HPC node-level parallelism in hybrid MPI plus threads models. Operating systems, multi-threaded kernel tasks and background services.